Hi everyone, I'm Lau Paxi Pers. Today I'm going to talk about a mathematical topic called sum of series. First of all, I will introduce you what a series is. A series is the sum of the terms of a sequence. We have the types of series which are finite series and infinite series. For finite series, we have defined first term and last terms. For example, summation of I from 1 to 100 is equal to 1 plus 2 plus 3 blah 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 plus 100. For infinite series, it continues indefinitely. For instance, summation of 1 over 2 to the power of n from n equals to 1 to infinity. It will equal to 1 over 2 plus 1 over 4 plus 1 over 8 blah blah blah. Before knowing sum of series, we have to know what a partial sum is. A partial sum is a sum of parts of a sequence. For example, we have a sequence of even numbers 2, 4, 6, 8, 10, blah blah blah. The first partial sum S1 is equal to 2. The second partial sum S2 is equal to 2 plus 4. The third partial sum S3 is equal to 2 plus 4 plus 6, etc. Then, what is a sum of series? We have two types of series called divergent series and convergent series. For divergent series, the limit of the sequence Sn is infinite or does not exist. For convergent series, the series Sn of partial sums has a finite limit. The expression below shows that we take limits to the sequence of the partial sum when n tends to infinity. So, if the limit of partial sum exists, it is called sum of series. Next, I will talk about Fibonacci sequence. It is a famous example. The definition is that f0 is equal to 0, f1 is equal to 1, and fn is equal to fn minus 1 plus fn minus 2, where n is larger than or equal to 2. So here, we have a sequence 0, 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, etc. In this sequence, you can see that the third term is the result of summation of the previous two terms, which means 1 is equal to 0 plus 1. And then you can see that 2 is equals to 1 plus 1, and it continues to form the Fibonacci sequence. Golden ratio is an important finding in the Fibonacci sequence. If we take the ratio of two successive numbers in Fibonacci series and we divide it by the previous number, from the calculation shown, we can see that the ratio seems to be settling down to a particular value, 1.618034, and it's called a golden ratio. Here is an interesting usage of Fibonacci sequence. Look at your hands and you have 2 hands, 5 fingers and 8 fingers are each comprised of 3 sections. Then, look at your index finger. From the tip to the base of the wrist, each section is larger than the preceding one by about the golden ratio 1.618 and also fits the Fibonacci numbers 2, 3, 5, and 8. So, talking about the sum of Fibonacci sequence, it is equal to summation of fi from I equals to 1 to n. Then we have fn plus 2 minus 1. The example here is the summation from I equals to 1 to 6, and it equals to 12. For the application of it, it is useful in converting the unit of km and mile. For instance, there are approximately 8 km in 5 miles. So, to convert 20 km to miles, we can express 20 as the sum of Fibonacci numbers, with 13 plus 5 plus 2 km equals to 20. It is around 8 plus 3 plus 1 miles and equals to 12 miles. Next, I'm going to discuss arithmetic series. In arithmetic sequence, the difference between two consecutive terms is a constant. In general, it equals to a plus d, a plus 2d, blah blah blah, where a is the first term and d is the common difference. Though we have finite and infinite arithmetic series, in this video, I will only focus on the finite one. For the sum of arithmetic series, we sum up and have the summation of a plus kd from k equals to 0 to n minus 1. Then, we get n over 2 times 2a plus n minus 1d. Here, it is the proof of the sum of arithmetic series. First, we add up all terms in the sequence and form Sn, which is the sum of the first n terms, and we call it number 1. Then, we reverse the order of 1 and get 2. Next, we add up 1 and 2. The first term in 1 is added to the first term in 2 and so on. Then 2Sn is equal to n times 2a plus n minus 1d. Then we have Sn equals to n over 2 times 2a plus n minus 1d, and we finish the proof. In this example, we have to add up the first 9 terms of 1, 4, 7, 10, 13, etc. We have a equals to 1, d equals to 3, and n equals to 9. We then plug in the values into the formula of sum of arithmetic series. We have summation of 1 plus 3k from k equals to 0 to 9 minus 1, and get 117 as the answer. After the arithmetic series, another essential series is called geometric series. In geometric sequence, each term is found by multiplying the previous term by a constant. In general, it equals to AR squared, AR cubed, etc. A is the first term and R is the common ratio. Here is the formula of sum of geometric series. We have summation of AR to the power of k from k equals to 0 to n minus 1. This equals to a times whole bracket 1 minus r to the power of n over 1 minus r. This is a proof of sum of geometric series. Firstly, we let Sn equals to a plus ar squared plus ar cubed blah 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 plus ar to the power of n minus 2 plus ar to the power of n minus 1, and we call this 1. Then we multiply Sn by r, and we get Rsn equals to ar plus ar squared blah 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 plus ar to the power of n minus 1 plus ar to the power of n. This is called 2. Next, 1 minus 2 will become Sn minus Rsn is equal to a minus ar to the power of n with the elimination of terms in the middle of the two equations. After simple calculations shown, we have the sum of geometric series equals to a times whole bracket 1 minus r to the power of n over 1 minus r. Here is the example of the finite geometric series. We want to add up the first 5 terms of the sequence. We find that a is equal to 8, r is equal to 3, and n is equal to 5. Then we plug in the numbers in the formula, then we get 968. We can find the infinite sum of series by differentiation. In the question, we have to find the sum of summation of n over 5 to the power n from n equals to 1 to infinity. From the definition, we have 1 over 1 minus x is equal to summation of x to the power n from n equals to 0 to infinity. Then we differentiate both sides with respect to x and get 1 over 1 minus x whole square equals to summation of nx to the power of n minus 1 from n equals to 1 to infinity. Next, we multiply both sides with x. Then the x to the power n minus 1 on the right-hand side will become x to the power of n. We plug in x equals to 1 over 5 and then get the result of 5 over 16. After that, I will talk about the applications of sum of series. Suppose you win the lottery and you will be paid 10 million over 10 years, in other words, 1 million per year for 10 years. If the money is invested at 8% interest rates, compounded annually, how much money does the lottery have to have saved up in order to pay you 1 million each year? So, if you invest an amount P at 8% interest rate, at the end of the year you will have P times 1.08. In order to pay you 1 year from now, the lottery people have to have 1 million over 1.08. The amount that needs to be saved in order to pay you 2 years from now will be equal to 1 million over 1.08 to the power of 2. Therefore, in order to pay for the nth year, there needs to be an additional 1 million over 1.08 to the power of n. The total the lottery people need to have now is 1 million plus 1 million over 1.08 plus 1 million over 1.08 square plus blah 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 plus 1 million over 1.08 to the power 9. Applying the formula of geometric series, then we can get 7,250,000 will be the answer. Now we can move on to the exercise part. Suppose that you are planning for retirement. You are able to invest your money at 10% interest rate compounded annually, and you would like to withdraw 40,000 per year for 30 years. How much do you need to have saved? So the amount needed to be saved will be equals to 40,000 times 1 minus whole bracket 1 over 1.1 to the power of 30 over 1 minus 1 over 1.1. Then this will be around 450,000. So this tutorial video is finished here. Thank you for watching.